if this has dimension n and this has dimension m, then that space of linear maps turns into a space of rectangular matrices. But do I actually have that many choices in this case? And the answer is no. I don't have free choices over anything in this column because everything in that column has to be 0. So how many free choices do I have left? And that's the answer to what the dimension of the space is. And the way that you think about it is you could freely choose. So any map that has zeros in the first column is going to send V to 0, but you could choose any of this entry can be chosen and this entry can be chosen by you. You could put anything you want at any of these other spots. And no matter what you put in any of those other spots, it's always going to be the case that this condition still holds. And so the number of free choices that you have left is not n by m, but we've sliced one of the columns off. So it should be the case that you should be able to convince yourself that the dimension of E is equal to the m rows that you got to choose, but n minus 1 columns. The column of zeros was forced onto you by the T of V is equal to 0, but none of the rest of the matrix is controlled at all. And so I hope this isn't too confusing, but the idea is that if you take this, if you take the operator T and you represent with a matrix, then the condition T of V is equal to 0 means you don't get any choice for how that part of the matrix is built. But you could pull the matrix apart into a bunch of coefficients where you get to freely choose every other spot. And that means you have m times n minus 1 choices left to make, which represents the dimension of the space. Does that make sense? Hopefully not too confusing here.
So is the dimension of this space kind of similar to like the ideas of like degrees of freedom?
Essentially, yeah, right. So you can, when you're working with a matrix where you have actual free choices at every spot, essentially, like, yeah, working in the background is free choices correspond to degrees, right? Like dimensions. I mean, the other way to think about it is if you actually wrote down a basis. So if you wrote down a basis for this, if you took a matrix, say that was 0, 0, 0, A, 2, 1, A12, A13, A22, A23, A32, A33, and you wrote down a basis for that space, you would write down A22 times 0, 1, 0, 0, 0, 0, 0, 0, 0 plus A1, so that's supposed to be A12, A13 times 0, 0, 1, 0, 0. I mean, and you go through this whole process, and by the time you're done, there'll be 6 vectors that you can use to build A33 times 0, 0, 0, 0, 0, 0, 0, 0, 1. This collection of matrices is actually the basis for this vector space. And how many of them are there? Well, there's one for each coefficient.
I have a question.
Sure.
So the matrix that you wrote above, m sub t equals to that. So that is the basis.
Well, how do you compute the matrix of a transformation? You take each element of the basis and you plug it in, and then you look at the coefficients of the vector that comes out, and that's what you write for that column of the matrix, right?
Yeah.
So that's how I did that.
Yeah, but my question is, so E is a set of vectors, right?
E is a set of maps. E is a set of maps. Yeah.
Yeah, and m sub t is a matrix of one map.
Of one map.
So how come the dimensions of this map?
Well, because because I wrote down T, but the only thing I specified about T was that T of V was equal to 0. So this T is arbitrary, right? T is some arbitrary map that takes V to 0. So any one of those maps is going to have, I mean, what's lurking in the background here is this fact. So the fact that the linear maps from V to W is isomorphic to FMN means that you can go back and forth from one space to the other. So as soon as I know the dimension of V is N and the dimension of W is M, I can think of the elements of LVW as being M by N matrices. And I can go back and forth from the maps to the matrices and from the matrices to the maps. Each map uniquely has a matrix, and each matrix uniquely represents a map.
Okay, so are you saying, I'm sorry.
No, this is hard. We're doing this stuff we're doing right here is hard. This is hard
So,
stuff.
are you saying that the matrix like on the screen represent all linear maps that are
No,
satisfying?
no. What I'm saying is this, like, so I'll be more concrete here. So what I'm saying is that if you pick a T, pick any T you want in E, which is a subset of LVW. And what that means is the matrix of T is an M by N matrix. That's just true, right? That's the isomorphism tells you, you pick a T inside E, the matrix of that operator must be M by N because it's a map from V to W, right? So that's step one. Step two is that particular T has a matrix that looks like this. T is, the matrix of T. If I pick the basis V, comma, V2, comma, V3, comma, Vn, then the matrix for T looks like 0, 0 down to 0. And then you can think of it as being the T1 entry and the T22 entry and the T32 entry down to the TM2 entry and then the T22 entry, or sorry, 1,3 entry and the T23 entry down to the TM3 entry, all the way out to TN, T1 n down to TMN. The particular coefficients here come from the map. These coefficients come from having made this choice, right? So you pick the T and then the coefficients are forced on you. But this is an isomorphism, which means every T gives you a matrix that looks like this, but every matrix that looks like this gives you an element T inside that space E that we can move back and forth from one to the other. So if I pick a T, it has a matrix that looks like that, but any matrix I write down that looks like that gives me one of the maps in E. That's what we mean by an isomorphism. Any matrix that looks like any T contained in E automatically is in one-to-one correspondence with a matrix that has a column of zeros and then a bunch of free choices other places. And by free choices, what I mean is if you pick the T, you're forced to get this matrix. But if you pick this matrix, it gets you a T back in E. That's what it means to be an isomorphism. Isomorphisms mean things are in one-to-one correspondence. So if you go forward and there's always a column of zeros, then if you write down a matrix with a column of zeros, you can always go backwards to have gotten the operator T that built that matrix. So each one of these matrices comes from a linear map, and each one of those linear maps goes to one of those matrices. And so if I can find a basis for this space, so this space has a basis that is m times n minus 1 dimensional. It's easy to write down a basis for this space because it's just a bunch of vectors. You pull it apart into these vectors that have zeros everywhere and a single one someplace. But if I have isomorphism between vector spaces, the dimensions have to be the same. So if this space is m times n minus 1 dimensional, that forces this space to be m times n minus 1 dimensional. I can't be more concrete than that, I'm afraid. I mean, I can do a specific example of it instead if you like, to give you an idea of exactly what's happening here. So let's just think about a matrix that would do this. Let's pick an L that takes R2 into R2, right? And let's say that so this is the big space we're living in, right? So just two-dimensional inputs and two-dimensional outputs. And let's fix a vector V in R2. And let's let that vector be equal to the vector, I don't know, how about 2, 0? There's a good vector. So let's let V be equal to this. And let's let E be equal to the space of every map in L of R2 to R2 that has the property that TV is equal to 0. So what we're saying is, if we pick a basis for R2 that looks like 2, 0, and I don't know, 0, 1, there's a good basis for R2. That's like our V1 and our V2. And I pick another basis for R2 for the output space. And for that one, let's just pick the basis 1, 0, 0, 1. Then what we're saying is the map of T, the matrix of T, would have to be equal to, like if I pick like an arbitrary T, I don't actually know what T does right now, but I know whatever it does, it has to turn this first vector into zeros. Has to. That's what it does. T takes that vector V and destroys it, turns it into zeros. That's the first basis element. So it gives me this column of zeros. What does it do to the second vector? I have absolutely no idea. None. So that means I don't actually know what goes in this spot, and I don't know what goes here. Because I didn't tell you what T was. I just told you it's a linear map. So I know it does something. I know it's got coefficients there, but I don't know what those coefficients are. So the space E is isomorphic to this family of matrices. So E is isomorphic to matrices that look like 0, 0, T1, 2, T2, 2. What's the dimension of this space? Well, everything over here can be written as T1, 2 times 0, 1, 0, 0 plus T2, 2 times 0, 0, 0, 1. And every single matrix here gives you a map back over here. That's isomorphism. If I start with one of these like maps in E, I can come over here to this matrix. If I start with one of these matrices, I can go back over here to find the T. Isomorphism means same. Having something on one side is the same as having something on the other, and I can go back and forth uniquely. This space is the span of the vector 0, 1, 0, 0 and 0, 0, 0, 1. And that means that the dimension of this space is 2, because there's 2 basis elements. So if this space is 2-dimensional and it's 1-to-1 correspondence with this space over here, then this space must also be 2-dimensional. That's how the argument goes. You just have to do it in the m by n case instead of the that's 2 by 2 case I'm describing right now. But this idea that like you can take the space of maps and think about them as equivalent to the space of matrices is a really important idea, that these are really the same space. E corresponds to some subspace of matrices. And if I can figure out what's going on in the matrices, I can take that structure and I can put it back over in the vector space that I started with. So understanding E is the same as understanding the matrices that represent it. I will put the addendum here that this takes some work to understand. So I'm already being quite a bit more verbose than Axler is about this, or any solutions you're going to read online about this question, which are just going to assert that the space of matrices with column equal to 0 is going to be n or m times n minus 1 dimensional. But implicit in that is the idea of moving back and forth using isomorphism. These notes are in the OneNote, so if you guys want access to it, then that's where it will be. But that's the basic idea of this question. This is not an easy question to get your mind around, but this is how the idea works. You come up with a map, show the matrix that represents it has some sort of special form, and then find the dimension of the set of matrices. And if you find the dimension of the set of matrices, then you knew the dimension of the subspace that it came from because they're isomorphic to each other. Follow-ups on that? If you're not following this question or you're wrestling with the ideas that I'm talking about here, make sure you come in. I mean, the idea of moving around with isomorphism, this is the first time a lot of you have seen this idea. Don't get dismayed if this looks incomprehensible. You just have to like do it enough that it starts to be comfortable. So if you don't follow what I just did right here, just come into office hours and chat with me again, and we can go line by line and make sure that we completely understand what's happening. Okay. All right, any other questions now that I've pulverized you with the answer to that one?
Can I ask you a question real quick? So just it's just that when you say like the matrix come from the T, right? Like each
Yeah.
T has a matrix. So that matrix becomes like I don't know if the word space is allowed to use, but like you know, like when you said the dimensions of a space, like that matrix has a dimensions.
No, the matrix lives in a subspace of matrices. If you have a subspace E, and you take every single one of those maps and you figure out what its matrix is, then that family, that set of matrices is also a subspace. If you started with a subspace and you go through an isomorphism, on the other side of that isomorphism, the subspace stays a subspace. So if E is a subspace of the linear maps, then the matrices of the maps in E are going to be a subspace of the m by n matrices. So if it was a subspace when it was maps, it's still a subspace when it's over in matrix land. Each map has one matrix that represents it, but the maps are a subspace, and that forces the matrices to also be a subspace.
Okay, thank you.
And that's what we're talking about the dimension of. All right, so if there are no more questions, I am going to move on with some, I guess last time what we were talking about, I'm going to remind you guys that last time we talked about the idea that an invertible map is equivalent, a map being invertible is equivalent to that map being injective and surjective. And then we also laid out the definition that two vector spaces are isomorphic if and only if there's an invertible map between them. And when a mathematician talks about isomorphism, frequently we abuse the idea slightly because we actually think of isomorphic objects as being the same object, but with different names. And I used that sort of idea when I was talking about the solution to this problem. When I'm thinking about the space E that we talked about right here as really being the same as a subspace of matrices. And that if I do anything in E, there's a corresponding idea in a subspace of matrices. And anything I say about the subspace of matrices is also true of the subspace E. And that's what the isomorphism gets you, is that these are really the same object with the same relations. So I'm going to see if I can make that more concrete now. So the first thing is, the first big question is, when are two spaces isomorphic? When are two vector spaces isomorphic? And the answer is, that is a question that is completely determined by the dimension of the spaces. And so this is the theorem. Two finite dimensional vector spaces are isomorphic if and only if they have the same dimension. And this is I think this is going to be the proof of the day. This is not a long proof, but we're going to walk through it anyway. And then I'm going to assign proofs to you guys for maybe the other theorems that I write on today. But this one has some nice ideas in it that I want you to have seen. So let's start with the forward direction here. So we're going to assume that we have isomorphic vector spaces. So suppose V and W are finite dimensional isomorphic vector spaces. So we're going to unwind what it means to be isomorphic. To be isomorphic means there is an invertible map. Invertible map T that takes V to W. Now we unwind one step further. So we started with isomorphism, and now we unwound that to mean there is an invertible map. But what characteristics does an invertible map have? Well, to be invertible means T is injective and surjective. But What does it mean? Again, I think I've emphasized to you guys a bunch already that you have to know your definitions, because all we're doing is unwrapping definitions here. Isomorphic meant there existed an invertible map. Invertible meant injective and surjective. What does that mean? Well, to be injective means that the null space of T is the 0 vector. And to be surjective, that's injectivity. And to be surjective means that the range of T is all of W. So how are we going to show that the ranges of V and W, or sorry, the dimensions of V and W are the same? We're going to use the fundamental theorem of linear maps. So we know that the dimension of V must be equal to the dimension of the null space of T plus the dimension of the range of T but that means that the dimension of V is equal to, well, the dimension of the null space of T is 0, because the null space of T was just the 0 vector. And the dimension of the range of T, well, the range of T is equal to W, so the dimension of the range of T is the same as the dimension of W. And so therefore, the dimension of V is equal to the dimension of W. So this is a straightforward direction that is just unwinding definitions and using the fundamental theorem of linear maps. Or if you're really attached to your 206 language, the rank nullity theorem. Okay, but the idea is you can actually trace what the logic is, because all we did was replace in each step what that meant. And then we just traced it down all the way until we got the result that we wanted from our big theorem. So if we are isomorphic, then our dimensions are the same. I should point out here that the general name of this idea, I've used the word here, this is called unwinding definitions. You're just going backwards from definition to definition until you get the condition that you need to solve the equation. Okay, in the other direction, we're actually going to exhibit a map. So in this direction, we're going to assume that the dimension of V is equal to the dimension of W. And in this direction, if I want to show that these are isomorphic, it means I actually have to find an invertible map from V to W. So what I want to do, so I want to show that there is an invertible map from V to W. And the way that we're going to show that is we're just going to write it down. So consider this map. Choose V1 to Vn to be a basis for V. And because V and W have the same dimension, then that means I can pick a W1 to Wn to be a basis for W. Those lists have the same length because the dimensions are the same, which is why I've used n as the subscript for both. And here's the map. So let T be the map that takes any linear combination of the V's and turns it into a linear combination of the W's. Now, if you remember, the very first thing we did in chapter 3 was show that this map right here was well defined. So if you look back at Theorem 3.5, we actually built some of the properties of this map. So why is this map surjective? Because it's easy to see how you would get an input from a given output. It's surjective because if I got a W, I could express W is equal to C1 W1 up to Cn Wn, but then that means T of C1 V1 up to Cn Vn is equal to W. And that means that any W is in the range of this T. You just peel off the coefficients and stick them on the V's. And if you took T of that, you would get your vector W back. And that means that this is a surjective map. Why is it injective? Well, what's the null space of T? So suppose that V is in the null space of T. That would mean that TV, which would be equal to C1 W1 up to Cn Wn, would be equal to 0. What can I say about the C's? Well, the C's must be 0 because W1 through Wn is a basis, and so it's linearly independent. But then, since W1 to Wn is linearly independent, C1 up to Cn are all equal to 0, which implies that the null space of T is just the 0 vector. So we have a map that is simultaneously linearly independent and surjective, and so, or sorry, that it's injective and surjective, and so T is invertible. But then that means that V and W are isomorphic. So this sort of argument is pretty standard when you're doing this kind of things. In one direction, we got to use this really nice geometric idea that comes from unwinding definitions and using the fundamental theorem of linear maps. That says, you know, if we know they're finite dimensional, then we can go backwards to show that they're, or sorry, if we know they're isomorphic, we can just use the fundamental theorem to show that the dimensions are the same. In the other direction, if I want to show that things are isomorphic, I have to actually show you what the isomorphism is. And that's what we did here. This map right here is the isomorphism. So this is the isomorphism. Isomorphic is the isomorphism. So if you want to show things are isomorphic, you actually have to write down, in many cases, you have to write down what the map is and show that it's the isomorphism. And that's what we did. We showed it was surjective, we showed it was injective, so therefore it was invertible, and that's the definition of an isomorphism. It's an invertible map from V to W. And so we conclude, well, we conclude by writing a little square at the bottom and filling it in because we're done.
Why do we never like use M, like the length of W?
Well, they're the same length. The dimension of V, the dimension of V and the dimension of W were the same. And so this number, yeah, so this number right here and this number right here, that they're the same number. So we don't, this is actually why this is the only reason why this works. This map that we defined right here, this map, if this was not, if these lists weren't the same, then this assignment I did right here doesn't work because maybe there would be extra W's left over that I haven't mapped onto, or there'd be too many W's and there'd be some that didn't pick up a coefficient somewhere.
Okay.
Right? So it's only because the lists are exactly the same length that I can say, take the coefficients from this basis and just stick them over here on this basis.
Okay.
It's a good question. Any other questions about that?
I had a question
Sure.
about the injective part. Like,
Yep.
how does this? I don't see how like to follow this. What you wrote down.
Okay, so let me see if I can be more clear about that. So what would it mean to be in the null space of T? It would mean that TV is equal to 0, right? That's the definition of being in the null space. If V is in the null space of T, then TV is equal to 0. But TV is also in the range of T, which would mean that whatever that vector happened to be, it could be expressed as a linear combination of the W vectors, right? So what we're saying is anything in the null space forces those coefficients as a linear combination of the basis. If you're in the null, like this particular setup right here, if 0 comes out and you have to express 0 as a linear combination of the W's, there's only one way to do that, which is all the coefficients have to be 0. W is a basis, right? but the coefficients on the W's were the same as the coefficients that originally existed on the V's because of the isomorph, because that we've assumed here that I mean, this is, but just we defined the map to do that, right? We defined the map to say, like, T takes in a vector V and it takes the coefficients of the V vector and it spits them out as the coefficients of the W vector. So where would this have come from? I mean, that's really the issue here. It's like, where would those coefficients have possibly come from? The fact that the W1 through the Wn are linearly independent means any linear combination of those vectors that adds to 0 gives you that those coefficients are 0. And that says that the only vector in the null space that's possible is the 0 vector.
Oh, I see now.
Yeah, the way I should have written it is like this. So I can actually fix this so it's clearer what's going on here. So what we're really saying is, if you're in the null space, then T of V is equal to 0, right? That's
Right.
that's what it means to be in the null space. On the other hand, TV is also equal to C1W1 plus CNWN, just as an element of the range, right? Anything in the range is in W and can be written as a linear combination of these vectors. So if you combine being in W with being in the null space, the equation you get is 0 is equal to C1W1 up to CNWN. So you're taking the null space equation and existing in the codomain and putting them together to say that you get this equation. And then you use linear independence to conclude that those coefficients must evolve in 0. And so the only vector in the null space is the 0 vector.
Okay, thank you.
Yep. Good questions today. Anything else? All right. So I'm going to finish up a couple of theorems here that I'm going to assign you guys to read the proofs of. In 3.60, it is very important to note that if the dimension of V is equal to N and the dimension of W is equal to M, we use this in the question that 2 asked earlier, that L of VW is isomorphic to FMN. And again, it's important to note here what that means is that any map here, any T, has a unique matrix over here that represents it, an M by N matrix. So A11 down to AMN is not an N. And that correspondence is a bijection, by which I mean, if you wrote down a matrix, you know that it came from a unique map. If you write down a map, it goes to a unique matrix. These are literally the same space mathematically. So we think of the space of linear maps as being identified with the space of rectangular matrices. I should point out here that this isomorphism, we have to be a little bit careful because the matrices, the particular matrix that you get, the matrix that represents T, depends on the basis you picked. And so later in the class, one of the things we're going to do is we're going to try to make this isomorphism as nice as possible. And if you guys remember back in the past, the idea of Gaussian reduction, or you remember the idea of finding eigenvalues and eigenvectors, a lot of that corresponds to making this isomorphism so that the matrices are as nice as possible, choosing a basis to make the matrix really nice. All right, questions about that? All right, last big idea here. And this is a huge one. So if we make the following designation here, this shouldn't be surprising to you. I can take a vector in a vector space, and I can think of that as a matrix. So any V in a vector space V has a matrix. And the way that you get it is like this. So we think of the matrix of V as being equal to C1 down to Cm, where V is equal to C1, V1, sorry, not V1. Yeah, that's right. Up to Cm, Vm. So I take V, I express it in terms of a basis, and then I take the coefficients and I pile them up into a vector. So as an example of how this works, I might say something like, what is this polynomial? How about 2z plus 1/2 of a z cubed in P3 of f? What's the matrix? Say, well, let's call this P. What's the matrix of P? Well, first we have to pick a basis for P, which looks like, I can use the standard basis here, 1z, z squared, z cubed. P is equal to 0 times 1 plus 2 times z plus 0 times z squared plus 1/2 times z cubed. We've got coefficients C1, C2, C3, and C4 times standard basis vectors V1, V2, V3, and V4. So the matrix for P should be the column vector consisting of the coefficients 0, 2, 0, 1/2. Okay, so when you're working with the matrix transformations, you can also represent not just maps, but the vectors in the vector spaces as matrices as well. So this is called the matrix of a vector. Okay, pretty standard sort of move. Most of you have seen this before in 206, but the idea is that, and the reason that you want to do this is because then it's going to turn out to be the case that what we're going to try to build here is the idea that if I have some map T in LVW, and I have some vector V in V, then taking T and applying it to V is in some sense isomorphic to, so I'm going to put isomorphic, to taking the matrix of T and applying it to the matrix of V. So linear maps turn into matrix multiplication. Okay, and that's the big deal when you're looking at say theorem 3.6.5, which says the matrix of a multiplication like this is equal to the matrix of the operator times the matrix of the vector. Okay, now I don't have enough time, I guess, today to talk about like some examples of that, but this idea right here is the core idea of why we think about matrices at all, is that anything that I can write down as a linear map on a finite dimensional vector space, any map can be thought of as multiplication by a matrix. So maps correspond to matrix multiplication, and that's going to let us study the family of linear maps of the concrete numerical object that we can work with computationally. And because of isomorphism, working in the linear maps on a vector space is identical to working with matrices acting on an Fn. So matrix multiplication on n-dimensional vectors that you know from your earlier classes. So this is like the core move of finite dimensional linear algebra. Sorry if you heard the door slam there. That was one of my kids racking on the door. So anyway, so thanks for hanging out with me today, guys. We'll be back in class for our regularly scheduled stuff tomorrow. I appreciate your patience with a brief virtual excursion, and I'll try to reschedule like an additional office hours to make up for the one that I missed today. But thanks for your patience. And yeah, I'm going to stop the recording.